Which is that right? Okay, good morning. Had coffee needed? Right. So, I think yesterday you should have learned how to make two-dimensional plots, contour plots, from the output of the Markov chain curve to plot confidence regions. And you shouldn't be able to do that, the Python guru no, from the chains run by the W. Martin. There was for a lambda CDM model adding an extra parameter, which is the effective number of continuous species. Did you manage to do that plot? No? Oh, well, okay. If you did, or if you did not, then I'll show you what you should have found. Okay, you should have found something like that. This is the value of H0, this is the number of effective species, then these confidence contours are a little bit bigger or a little bit smaller depending whether you use the chain that have only the temperature and the polarization only at low L, or whether you use the one that also have the polarization at high L, but you should have found something like this. And the constraint from the local H0 measurement in this plot will just some vertical band centered around that measurement. Now, in order not to spoil the surprise, what I showed here is the old measurement, not the new measurement. But, you know, you can see what happened. Oh, you get something similar?
Yeah, but I was wondering which data set is this because I have a lower value for the other side, like 5.7.
Maybe because,
Maybe, but it's maybe the data set. Right?
maybe it's a data set. That's what you should. You should have something that looks like that. What do you think would happen if you combine something like this with something like that? Again, you don't need to do the analysis again. One of the possibilities to do product sampling, which we saw yesterday, take the weight and re-weight them by the new likelihood and find something like that. So to see what we are getting at, I may show you actually a plot from a paper. This is the papers of recent collaborators where they actually report the new measurement of H0 and they do exactly the same plot. H0 here and then effective here. They use a slightly different combination of data sets. So they use Planck plus Verde plus supernovae, and in Planck they don't use the higher polarization, which is 10% lower polarization. But also use Verde or supernovae, which has information about the polarization universe, and when they add H0, then it's strange. Also because H0 is set around 73, while the CFE plus blood is set around 68. Okay, so keep this picture in mind because we're going to come back to this later on. What I would like you to do now, since we went to Fisher matrices, is to try to implement a simple Fisher matrix for something that could be like H0. So if you remember, this is the Hubble law. It says that the recession velocity is directly proportional to the distance of objects. And what Hubble had was sort of plot like that, where it had recession velocities down here, distances up here. This is a very nice way of putting it, even the other way you measure 1 per h naught, because there's very little error in measuring the redshift, but there's a big error in measuring distances, and so here you have to be very careful there, not only go this way or that way. So if, for this example, assume that all your data points will have the same error, sigma, and assume that the errors are constant. And so this may sound familiar. I actually recycled the same images we used when we were introducing the chi-square, because this is like doing a linear regression. Your model is y is equal ax plus b. You may want to add b or may not. In the other law, there's no plus b, so you may want to have only one parameter, or you may want to say, can you put some extra nuisance parameter, maybe I can calculate it up and down, whatever, and then we will add extra parameter, and we say it will be 1 h naught. And now, the question you may want to ask yourself is, how many data points would I need to get a given error on h naught depending on sigma? Or how would I want to distribute my points in here to get a nice error on h naught? And the hint here is resource efficient. You don't need to do the experiment. You don't need to simulate many supernovae or whatever happens using to do that. You just have to do it in a paper. And so before I show you the solution or the step of the solution, I would like to give you a little bit of time to think how you would frame the problem. So if you were to frame the problem in terms of efficient, how would you do that? So think about it for 2 minutes, write on a piece of paper how you would do it, and then I unveil the result. So you should have by now the element of your efficient matrix. That's the efficient matrix is going to be a 2 by 2 matrix if you want to carry A and B. The 2 diagonal elements are going to be this one and this one. And the 2 off-diagonal elements are going to be this one, these 2. So remember, if you don't have B, you only have A. It's like taking the conditional error, and therefore you only take this, and then the error of the slope is 1 on the square root. Of course, it will depend both on the error, how many points you have, and where you put the points. It's not the same thing to compute the slope if you have 1 point very near to the origin as if you have 1 point far away from the origin. Makes sense. If you have both parameters, both A and B, then you have to deal with the 2 by 2 efficient matrix. And remember, if now you want to compute the covariance matrix, the matrix of the errors or the variances, you have to do a matrix operation to the efficient matrix. That famous matrix operation by an inversion. So you write the matrix, you invert the matrix, then once you invert it, the diagonal term are going to be the square of the marginal error on A and B. And the off-diagonal term is going to tell you about the correlation between A and B. Of course, if you are not satisfied with getting the efficient matrix this way, you can also get it this other way, which is what is written there. And if we look at this for more than a second, we realize that a lot of this term dropped out. This drops out, and we're just left with this one. Then of these that we only care about the diagonal part. And so you don't care what's going to happen to a point meets I, point meets J, so first and the third point of your array, you're only going to care about point meets I. And so here you're going to have, for example, for the A terms, it's 1 square, it's 2 square, it's 3 square. And now this one is 2, this 2 is 3. Which you have if the variance of over here. That was the okay. Let me leave you with that for now and move on and give you a more complicated exercise. So I may give you some time to do it, but you may want to finish it later in your own time. What I find interesting of this exercise is that it's basically a paper. The entire paper was this Fisher matrix calculation. And it was a Fisher matrix calculation of one variable. So that's how it works. Implement a simple Fisher matrix for non-Gaussian yellow values. So it turns out that if there is some non-Gaussianity of a special type, which is called local type, in the initial condition, you may actually end up seeing this effect by looking at the power spectrum of clusters. And I'm not going to go through the physics of that. I'm going to just tell you what the effect of this premature non-Gaussianity is on some observer. So what happened basically is that there is a correction to the bias of this object, halo clusters, that depend on the non-Gaussianity parameter, which is called FN. For those of you who are not fan of non-Gaussianity, I just ask you to do a Fisher matrix for FN. Recall that the bias, it's something that you multiply, something you square it, you multiply by the power spectrum, and you say the underlying power spectrum of matter multiplied by bias squared, give me the power spectrum of what I observe. And usually, if we have Gaussian fields, B is just a number, it's a constant. What this shows is that in that case, B is not a constant because it has a correction that goes like 1 over k squared. So as you can imagine, 1 over k squared, a very small k, blows up. So there is a large correction to the bias at very large scales. And the other thing you may want to know is that this delta C is the threshold of allowed, the one who have done threshold over this, the one who have not done it is just a function which you will find in the directory where the exercise files. And all the other cosmological parameters are fixed, so you have to do a Fisher matrix only for one number. And basically, that's that paper. Of course, there was more sophistication put in. It's like, let's take this survey, and how many redshift they have, and what's the volume, and what's the dependence as a function of redshift, and so on and so forth. But the concept is there. So, okay, so where do I start? Try what you need. You need log likelihood. And then you need to take the second derivative of that. What is that? Well, we already there already. For a single node, is that. We brought this because when we were dealing with constellation Gaussian field, so we're dealing with the PF Gaussian field. In this case, the field, yeah, is not Gaussian, but the non-Gaussianity is small, so you can still write down something like this. And take the log, sum over the modes, and take the derivative, And you end up with something like that. So your log likelihood is this, where these are the parameters of interest, and this is the power, and you're summing of the. Now, since we have only one parameter, we have to take a second derivative with respect to FNL. So now the next thing we need to do is we need to write what the power spectrum of halo is as a function of the underlying power spectrum, corrected by this delta bias that I did before. So I can repackage this, and the derivative is just that. For one node, just square this and you're done. For more nodes, you have to sum over the nodes. For, if you want to divide this surface in Redshift things, you end up with an equation like that. So that's for one Redshift thing. And then if I want to sum over Redshift thing, if the Redshift thing are independent, you just okay, now we're going by the thing. Exactly, it's not 2008 anymore, so now that's old. Okay, the other thing I want to mention is that sometimes you may want to do forecast for bioacoustic oscillation circuits. And there the things become a little bit more complicated because you know that the BAO feature measures something different in the line of sight across the sky, and so you can't do spherical average calculation, and you may want to take into account the dependence on redshift, the dependence on linear evolution, and all sorts of other things, but it's very nice because Serra and Eisenstein published a little C routine that actually does that for you. You would have to give them an input, that is how much of noise your survey has, what type of galaxies you want to use, what you think the nonlinear corrections are, etc., etc. But with this, it just spits out the Fisher matrix from which you can compute the error bars on dA over RS and H times RS, which is what the BAO can do without even having to do so. And so, for example, you can study how well you can constrain this quantity as a function of the volume of your survey, shot noise, the redshift range, and all that. So what I would suggest you to try to do is, the Python person is here, and I don't know if it was thinking about doing something like that or not. Python can be used like a glue to call codes, different codes from different even languages. And so here are two copies of the same routine. One is the original one produced by Serra and Eisenstein, where your code would have to pass internally to that routine the input values. And for that, you need to write more than one line of Python. However, this is my simplified version where this code reads all the inputs from a file. So your code in Python, IDL, Fortran, or whatever simply has to prepare an input file for this other thing, and then just compile that and use the compiled code that just read from the file and save the results on a file, and then you are done. That should be much easier to do. It's just an equivalent of a quality standard. You call it Python. So what I suggest is that you maybe open or either this file or this file and look at the instructions. This file are very nicely commented out, even though it's C. Just read the comments. So you see what's going on, and towards the end of the file, it just tells you what the element of the, in which form it gives you the element of the Fisher matrix. some redshift range limits. So now this is telling you there's no point to insist in improving the number density beyond 10 to the minus 3 because by that time you gain subsets. And you're calculating by variance. By the time you sparse sample it, you end up then calculating by points. And so the next thing I want to ask you is, can you think of example where Fisher fails? And that's an example, of course. So if you have a chi-square in this case, a log life that goes like this, then of course with Fisher you may sit around here and expand as a quadratic, which will work fine as long as you remain around here, but the point you go beyond this point, then of course the Fisher fails. So this is a typical example where the Fisher fails. This is a one-dimensional plot of some parameter versus delta log life. This is chi-square. Since we are assuming that everything is that the error are Gaussian and that the variance does not depend on the parameter, this is what it is. And so if I was sitting here and say this is my differential model, and then I forecast errors of this parameter, what I'm doing, I'm approximating this as a quadratic, as a parabola. And it works quite well on this side, but it does not work quite well on this side. So as long as you say within 1 sigma, that's fine. But if you want to go beyond 1 sigma or beyond 2 sigma, then you're lost, right? Because your parabola approximation will go on like that, and you will say, aha, this value of minus 0.4 is highly disfavored. Look at my delta chi-square, it's something like 12. It's not, because for some reason, this goes down again. And so actually this point is more favored than that point. Or, given that the delta chi-square is even squinting, I can see the difference, then it will affect. Okay, so there is one last thing I want you to do and say, so you got a Fisher matrix, that's what Antonio gave you in his paper from table 11 of his paper, and he gives you that. So for example, it gives you dA, normalized by this fiducial R and RD and fiducial RD, and H ratio. But look at what form it gives you the Fisher matrix. It gives you the measurement. You can do, for example, low Z, but you can also do Z mass sample, which is smaller than ours. It gives you the Fisher matrix in this form: measurement plus or minus error, measurement plus or minus error, and some sort of correlation coefficient. Is that a Fisher matrix? Not yet. You have all the information to write a Fisher matrix, but this is not a Fisher matrix. So actually, so what is this? This is the cross correlation between parameter this and that divided by this times this. So these are the plot that go under the table. Let's see what you can do with this. So you have a data vector which is dA and H measured. I'm assuming a res equal a res fiducial. You can always rescale, but for simplicity let's do that. And these are these two numbers. This is C, this is low Z, and the positive extraction. And then it gives you all the information to write down the variance matrix. In the diagonal, you should put the error square. And in the off diagonal, we should take this number and multiply by these two numbers. Now, this is not yet a Fisher matrix. This is an inverse of a Fisher matrix with Fisher matrix is actually the covariance to the -1. That's the Fisher matrix. So I basically undone what Alan told you to do. Once you have the Fisher matrix, how do you get the average? Fine. Now, the next thing I would like you to do is, well, you have the Fisher matrix, produce the typical ellipse plot. Find the 2D joint ellipse contour that includes 68% and 5%, plot the marginalized 1D distribution, etc. So how would you do that? Well, you have two ways of doing that. One's the hard way, one the simple. Now, depending which one is hard and which one is simple, it depends a little bit on you. Whether you like to do things by hand or whether you like to figure out how somebody else's code works and run. So, the way I see things is that, well, once we have this, then we can write likelihood opponent, which is take everything Gaussian, it's e to the -1/2, mu is data minus this, is dA and h the variables, the quantity you want to plot, and d was the measure, and then this f is this f you just found, and that's okay. And now you have all you need to do all the counter plot. Because you go to numerical recipe, you go to this very nice table. This is basically, if you take the log, this is a chi-square, so you just read from that table how, what's the delta chi-square that corresponds to the 68 and what the delta chi-square that corresponds to the 97. So if you do that, you get a plot like this. This is just a screenshot from my screen. And if you squint and actually try to compare with this, they're not exactly the same. They're very similar at 1 sigma, but they are different at 2 sigma. And now the question for you is, why do you think is that? Because if you ask Antonio, this contour here didn't come from that. This contour came from a real LCMC. So this is how the posterior is, which is not really Gaussian. As you know, no Gaussian is got this triangular shape. But what you've done with Fisher, you say, well, let me measure the curvature around the maximum and then approximate with a 2D Gaussian. And therefore that's why these contours are not coincident with this contour. At 1 sigma they look very similar, at 2 sigma this is sort of fine, this is fine. Now, the question for you is, what would happen if you would do the same with CMAS? There's much more data, much more signal noise in CMAS, and the upshot is that Fisher is going to be so much better approximation. Now, that's the way that is easy for me, but for other people it may not be that easy. The other way is just go to the Danco website, download this Fisher.py, give it the Fisher matrix, and tell this Python code to the ellipses. And so that's the other thing you will make. So I think I'll stop here.